Today we are going to discuss about gain margin, phase margin in Bode plot. Gain margin. Gain margin is the open loop gain, static gain that can be increased. The amount of static gain that can be increased so that the system will be in the verge of instability. That is called gain margin. In Bode plot, we can find the gain margin in decibel scale. To find the gain margin, we have to consider both magnitude plot as well as phase plot together. This is the Bode plots for phase and magnitude of a system whose open loop transfer function is 1 upon s multiplied by s plus 1 multiplied by s plus 2. This is the open loop transfer function. For that, this is the top one is the magnitude plot and bottom one is the phase plot. Both has the same common x-axis. Y-axis having different scale. For magnitude plot, it is in decibel. For phase plot, it is in degrees. But x-axis is common. This is not 1. This is 0.1. This is 1. This is 10. Here, the first step is to find the gain margin is the phase plot at 180 degree. Draw a horizontal line at 180 degree. That cuts the phase plot at A. Draw a vertical line at A that will meet the magnitude plot at B. At B, draw again another horizontal line to find the magnitude at B. The magnitude at B is minus 15.57. Therefore, the gain margin equal to minus of minus 15.57 equal to 15.57 dB. That is the gain margin. The meaning of this gain margin is if we increase the static gain in the closed loop, that is 15.57 dB, closed loop gain is increased, static gain is increased, then the system will be in the verge of instability. That is the meaning. It is in decibel scale. This is equivalent to finding the gain in root locus or Routh array. It is equivalent to finding gain in Routh array, that is Kmax. For Kmax, the system will be in the verge of instability and its poles will be on the j omega axis. The poles will be on the j omega axis. That Kmax we can found by Routh array. That is, the poles will be exactly on the j omega axis. This is third order system. That's why one pole is at origin, another pole at minus 1, and the third pole is at minus 2. Between minus 1 and 0, it is part of root locus because 2 is the right odd number of poles. Similarly, after minus 2, it is part of root locus up to minus infinity. There is a breakaway point and it goes to right hand side. The poles will be exactly at the j omega axis at Kmax. This Kmax can be found by Routh array. What is the denominator polynomial of this system? The denominator polynomial of open loop system is s cube plus 3s square plus 2s This is open loop transformation. Numerator k. As k varies from 0 to infinity, we got the root locus. Therefore, denominator polynomial, characteristic polynomial is s cube plus 3s square plus 2s plus k. That is written here. For that, if we form the Routh array, coefficient of s cube is 1, coefficient of s square is 3, coefficient of s is 2, then constant term is k. If you find this is s cube row, this is s square row, s power 1 row, if you find, what you will get 6 minus k divided by 3. 6 minus k divided by 3. S power 0 row, s power 0 row is, you multiply these two minus 0, 3 multiplied by 0 is 0, divided by k is, you will divided by 6 minus k divided by 3 is, you will get k again. So for a stable system, this first column of a Routh array must be positive. Therefore, the condition is k must be greater than 0. The second condition is 6 minus k by 3 should be greater than 0. That is 6. K should be less than 6. K should be less than 6. Therefore, when k is between 0 and 6, the system will be stable. When k equal to 6, that is k max. K equal to k max equal to 6, the poles will be exactly on the J-max axis. The system will be in the verge of instability, that we know. The same can be found from gain margin. Gain margin, how much? That is 15.57. This much is the gain margin. If we increase the gain of the system by this much, then the system will be in the verge of instability. That is in logarithmic scale, that is decibel scale. This is in dB scale. To find the linear gain, 20 log k equal to 15.57. Therefore, k equal to 15.57 divided by 20. If we take anti-log on both sides, k equal to 10 power 15 by 20. 10 power 15.57 divided by 20. That is equal to 6. We got the same answer. In both methods, it means gain margin means the amount of gain that can be increased in a closed loop system so that the system will be in the verge of instability. That is, the poles will be exactly on the J-max axis. The gain will be k max. That is the meaning of gain margin. This can be found this way. Similarly, if you increase any further above 15.57, the system will become unstable. The system will become unstable. In the same way, we can find phase margin. The same way we can find phase margin. To find phase margin, at 0 dB, we have to draw a horizontal line. To find phase margin, we have to start in magnitude plot. To find the gain margin, we have to start in phase plot. Just opposite. So draw a horizontal line at 0 dB. It meets the magnitude plot at C. At C, draw a vertical line. Draw a vertical line. It meets the phase plot at D. At D, horizontal line. Draw a horizontal line. That gives the value phase at D. The phase at D is minus 126.55. Therefore, phase margin equal to 180 plus 5. That is 180 minus 126.5. That is equal to 53.5 degree. That is the phase margin. The meaning of phase margin is, suppose we are having a system like this. We are having a system like this. R of S, K. This is the open loop system, G of S. Now it is in closed loop. If you increase k, that is k max equal to 6, the system will be in the verge of instability. It will exhibit sustained oscillation. Or without increasing this gain, you are not increasing the gain, keeping the gain as such. As such, that is in this case 1. But if you increase the phase shift, if you increase the phase shift of the system by 53.5, if you increase the phase shift to 53.5 degree, then also the system will be in the verge of instability. So without increasing the gain, if you introduce the phase shift in the system, additional phase shift of minus 53 point, that is very important, minus 53.53, 53.5 degrees in phase shift, then also the system will be in the verge of instability. That is the meaning. So therefore, it requires additional phase shift to drive the system in the verge of instability. If you see the gain margin, it requires additional gain of 15.57 dB to drive the system in the verge of instability. Both gain margin and phase margin are positive. Gain margin is 15.57, positive value. Phase margin is 53.5, positive value. Both values are positive. Therefore, the given system is stable and has a gain margin of 15.57 and phase margin of 53.5. If any of these values are negative, the system is unstable. Already it crossed j omega axis. That is the meaning. The system is in the unstable region. If it is negative, any one of these two are negative or both are negative, the system is unstable. The system is unstable. Here, to find gain margin at minus 180, we have drawn a horizontal line. It cuts A. It cuts the phase plot at A. The frequency at the phase plot A is called phase crossover frequency. So we have to find the gain margin at phase crossover frequency. At phase crossover frequency. Phase crossover, it crosses 180 degree. Phase crossover frequency. Similarly, at 0 dB, if you draw a horizontal line, it cuts the magnitude plot at C. At this frequency, we have to find the gain, that is minus 126.5. We found that C is called omega GC, gain crossover frequency. Gain crossover frequency. We have to find the phase margin at gain crossover frequency. So that's why the phase crossover frequency is to find the gain margin. Gain crossover frequency is to find the phase margin. Let us increase the gain. We know that the maximum gain is 6. The gain should be less than 6 for a stable system. Now let us increase this gain from 1 to 15 and we will draw the Bode plot and check the gain margin and phase margin. This is the plot for 15. The gain is increased to, static gain is increased to 15. For that, we have drawn the Bode plot, magnitude plot, as well as phase plot. Phase plot. Draw a horizontal line at 180 degree. 180 degree. That cuts the phase plot at A. That is called phase crossover frequency. In this case, this is 1, this is 2, this is 1.5 radians per second. So, phase crossover frequency, omega PC is 1.5. Draw a vertical line. It cuts the magnitude plot at B, omega PC. At omega PC, draw a horizontal line. Draw a horizontal line that meets y-axis at 10. Therefore, gain margin equal to minus of plus 10, that is equal to minus 10, negative value, therefore unstable system. Gain margin is negative because we increase the gain to 15. Maximum gain is 6, but we increase to 15. That's why uh, this becomes unstable. Let us find the phase margin. At 0 dB, draw a horizontal line. At 0 dB, draw a horizontal line. It cuts a magnitude plot at C. Draw a vertical line at C. Draw a vertical line at C. It meets the phase plot at D. Draw a horizontal line again at D. This gives minus 200 degree. So what is the phase margin? Phase margin equal to 180 plus 5. That is equal to 180 minus 200. That is equal to minus 20 degree. That is again negative. Therefore, the system is unstable. We know that if we increase beyond 6 dB, this will be unstable. We got the same. So the point D is called gain crossover frequency. Gain crossover, gain omega GC. If omega GC is greater than omega PC, unstable, we can easily say. Omega GC is greater than omega PC, then also we can say that unstable. Here you see that omega GC is less than omega PC. Here omega GC is greater than. That's why we can say that way also we can say the system is unstable. Negative value says unstable. That's all about gain margin and phase margin. Another way of understanding phase margin is we know that the Nyquist plot, polar plot for the given system. This is the polar plot for 1 by s multiplied by s plus 1 multiplied by s plus 2. Order is 3, type number is 1. Order is 3, type number is 1. 0 degree, 180 degree, 270 degree, 360 degree. Or you can say that minus 90, minus 180, minus 270. Like that we can say. So here modulus of g of j omega equal to 1 upon omega square root of omega square plus 1 square root of omega square plus 2. If omega equal to 0, it becomes infinity. Angle of g of j omega. This is the polar plot. Or can call it as Nyquist plot. It is part of Nyquist plot. So it can also be called as Nyquist plot. When omega equal to 0, angle equal to minus 90 minus tan inverse of omega minus tan inverse of omega by 2. If omega equal to 0, you will get minus 90 degree. So magnitude is infinity, angle is minus 90. That's why it is coming from 90 degree at infinity. When omega equal to infinity, what you will get? The modulus of g of j omega. When omega tends to infinity, what you will get? If we substitute infinity, it becomes 0. Angle of g of j omega, what you will get? Angle of g of j omega equal to omega tends to infinity. You will get this is also minus 90, this is also minus 70. Therefore, minus 270 degree. Minus 270 degree. minus 270 degree. So we got this plot. For intermediate values are lies in between minus 90 and minus 270. Magnitude also from infinity to 0. You got this plot. This is plotted on a polar chart. This is the unit circle. This is the unit circle. This is the unit circle. Minus 1 plus 1 plus j minus j. This is one. That's why stable system. That's why it doesn't encircle. It doesn't encircle the minus 1. Therefore, stable system. Stable system. If you increase gain, it will amplify like this. It will amplify. If you increase the gain to 6, it will pass through this way. If you increase gain to 6k equal to 6, if you increase k equal to 6, it will pass through minus 1 and it becomes in the verge of instability. In the same way, we can say that if you increase the phase shift, now the phase shift is at this point minus 126.5. If you increase the phase shift to another 53.5, minus 53.5, this point will move along this unit circle to minus 1. That's why if you, without increasing gain, if you increase the phase shift to 53.5, the system will be in the verge of instability. If the plot passing through minus 1 means it is in the verge of instability. If it is passing before minus 1 means stable. If it is passing after minus 1 means unstable. So if you increase the phase shift by minus 53.5, this point will move along this unit circle and it will reach minus 1 without increasing gain. That is to understand what is phase margin. So if we can explain phase margin by using polar plot or Nyquist plot easily. Nyquist plot easily. That's why I explained this with the help of Nyquist plot.